In machine learning, linear regression is a fundamental algorithm used for prediction. For a single feature, the model is a simple line. Here, theta sub 0 is the intercept and theta sub 1 is the slope of the line. But what if we have multiple features like the size, number of bedrooms, and age of a house to predict its price? Writing equations like this becomes cumbersome. This is where matrix notation becomes incredibly powerful and elegant. Matrix algebra provides a unified framework that scales beautifully from simple to complex models. We can express the entire set of predictions for our dataset with a single compact equation, the hypothesis function. Let's break down what x and theta are. First, we have the parameter vector theta, which holds our model's coefficients. Next is the design matrix X. Each row is a data point, and each column is a feature. We add a column of ones to account for the intercept term, theta 0. When we multiply x and theta, we get our vector of predicted values. Notice how each prediction follows our original linear model formula. To find the best line, we need to measure the error of our predictions. We use a cost function, typically the sum of squared errors. This penalizes large errors more heavily than small ones. In matrix form, the vector of all errors is simply our predictions, x theta minus the vector of actual values, y. To get the sum of squares of this error vector, we take its transpose and multiply it by itself. This is equivalent to taking the dot product of the error vector with itself. This gives us our elegant final cost function in matrix form. Our goal is to find the theta that minimizes this function. To minimize the cost, we use calculus. We take the gradient of j with respect to theta and set it to 0. First, let's expand the expression using matrix algebra rules. Using the property that the transpose of a product is the product of the transposes in reverse order, we can rewrite the transpose of x theta minus y. This gives us theta transpose times x transpose minus y transpose. Now we multiply the terms out. Just like foiling in algebra, we get 4 terms from this multiplication. A key insight, the term y transpose x theta is a scalar, a single number. The transpose of a scalar is just itself, so it's equal to theta transpose x transpose y. Since both middle terms are identical, we can combine them into -2 theta transpose x transpose y. Now our cost function is ready. The next step is to compute its gradient with respect to theta using matrix calculus rules. We take the gradient of j with respect to theta. We apply standard matrix calculus rules term by term. Let me show you each rule we'll use. A gradient of the first term, theta times a theta, where a is x times x, gives us 2 times x times theta. The gradient of the second term, -2 theta times b, where b is x times y, gives us -2 times x times y. The last term is constant, so its derivative is 0. We can simplify by factoring out the 2 and canceling with the 2 in the denominator. To find the minimum, we set this gradient to 0. This is the critical step in optimization. Multiplying both sides by m and rearranging, we get our key equation. To isolate theta, we multiply both sides by the inverse of the matrix x transpose x. This assumes that x transpose x is invertible, which is true when our features are linearly independent. This is the normal equation. It gives us a direct, analytical solution for the optimal theta values, without needing an iterative algorithm like gradient descent. A common student question is why not always use this? This method involves computing a matrix inverse, which can be computationally very expensive for datasets with a large number of features. This abstract equation actually contains the familiar formulas for slope and intercept. Let's prove it for the simple case with one feature. This derivation shows the beautiful connection between matrix algebra and classical statistics. For simple linear regression with one feature, our design matrix X has m rows and 2 columns. The first column is all ones for the intercept. First, we calculate X transpose X. This involves matrix multiplication of X transpose with X. Next, we calculate X transpose Y. This gives us the sums we need for our final formulas. Plugging these into xt x theta equals xty gives us a system of 2 equations. This is where we transition from matrix form back to scalar equations. This matrix equation represents 2 scalar equations that we can solve simultaneously. Let's write out the first of the 2 equations and solve for theta 0. We can solve for theta naught by rearranging the terms. We isolate the theta naught term on the left side. Dividing by m, the number of data points, gives us a familiar expression. Recognizing that sum of y over m is the mean of y, denoted y bar, and sum of x over m is the mean of x, denoted x bar, we get the formula for the intercept. Now for the slope, theta 1. We substitute our expression for theta 0 into the second equation from our system. This is where the algebra becomes more involved. After substituting theta 0, we get this rather long expression. Don't worry, we'll simplify it step by step. Let's distribute the sum of xi and then group all the theta 1 terms on one side. Isolating theta 1 gives us this fraction. It might not look familiar yet, but this is the correct answer. Now comes the beautiful algebraic insight. We can rewrite both the numerator and denominator in terms of deviations from the mean. Let me show you key algebraic identities. Similarly, the denominator simplifies to the sum of squared deviations from the mean. This gives us the well-known formula for the slope in simple linear regression. These formulas have beautiful statistical interpretations. The slope formula is the ratio of the covariance of x and y to the variance of x. Therefore, our slope can be written as covariance over variance, which shows it measures how much y changes per unit change in x. The intercept formula tells us that the regression line always passes through the point with coordinates x bar, y bar, the center of mass of our data. Let's recap our comprehensive derivation. We started with the goal of minimizing the sum of squared errors using matrix algebra. Using matrix calculus, we derived the normal equation, a powerful general solution for linear regression that works for any number of features. Then, by applying this to the specific case of one feature, we proved that it yields the familiar formulas for the slope and intercept. We also discovered the statistical interpretation. The slope is the ratio of covariance to variance, and the line passes through the center of mass of the data. This demonstrates the power and consistency of using matrix algebra to solve problems in machine learning. It provides a solid foundation for understanding more complex models like multiple regression, polynomial regression, and even neural networks. Thank you for joining me on this comprehensive journey through linear regression using matrix algebra. I hope this step-by-step derivation has deepened your understanding of both the mathematical foundations and the elegant connections between matrix methods and classical statistics.